We are now going to see how to compute the volume of a solid of revolution. What do I mean by that? This is a volume obtained by rotating a plane region around an axis. For instance, let's take a bowling pin. We can think of this bowling pin as having been obtained by rotating a region that roughly looks like this. And again, I'm being a little bit sloppy here, but think of this region and rotating it around the axis of the bowling pin itself. If you rotate it all the way around, then you end up with that solid. In the same way, and by rotating different kinds of regions around different axes, you could obtain something like a glass of wine or a bottle, or maybe some vases or a donut, or well, I must be obsessed with food these days. Or a volcano. Well, a volcano is not exactly a solid of revolution, but you get the idea. It's still something which has some kind of a circular rotating symmetry. Now, how are we going to do this? By again using the slice, approximate, add up, and take the limit process. Again, we're going to apply it to our whatever region we're rotating, but we're going to do that in several different ways depending on what kind of solid we have. As you notice, some of the solids you have in front of you are true solids in the sense that they're all filled in. Some have holes in them. Also, we're going to see that it will depend also on where the axis of symmetry is located. So let's have a look at these different methods. The first method we're going to see is called the disks method, and the reason is quite obvious. It uses disks. Let's see how that works. So first of all, what we're going to do is we're going to rotate some kind of region. And for now, we're going to assume that this region is of a special kind, similar to what we saw in the definition of the area of a plane region by using definite integrals. Namely, it's going to be bounded by a curve, f of x, in between two values a and b, and by a flat boundary on the bottom. Not only that, but we're going to assume that we're going to rotate this region around a horizontal axis that is actually part of the boundary. We're going to use the line that runs through the bottom boundary as the axis of rotation. By the way, more generally, we can see other situations where the axis of rotation sits on a boundary which is the top boundary, and the idea will still be pretty much the same. And the formula will be the same, except that it's going to be implemented in different ways. So the region looks like this. So this is the region we're going to rotate it. So now just imagine, use your imagination to think of this particular region rotating around that blue line, and think about what you're going to get. What you get is something that will look almost like this, and I'll leave it up to your imagination to figure out what this is. It's sort of the ending part of a tuba, maybe, or something like that. But that is the volume that we want to compute. Well, how we're going to do that? Well, so we're after the volume, and we're going to go back to our region and see how we can use our slice, approximate, add up, and take the limit method. As we go back to our region, we're going to first of all draw our slice. So it's going to look like a regular slice, and I'm going to indicate the height of this slice by r, not by f of x, because it is not, and not by h, but I'm going to denote it by r, and you'll see in a second why. Now remember, what we're doing is we're using this slice to approximate what happens when the whole region rotates around that axis. Well, what happens when we take this particular slice, and remember we're approximating by using a rectangular slice, and we're going to rotate it around that axis? Well, when we approximate it, what happens is that the region we obtain is going to look like, yes, you guessed it, a disk. And so what we need to do now is compute, or go back to review, what is the volume of a disk. Well, a disk is pretty much a cylinder, and therefore its volume is going to be given by the area of the base, which is a circle, so pi r squared, and that's the reason for my calling the height of that slice r, times the height of the cylinder. But the height of the cylinder is just the thickness of our slice, and this is what we traditionally call delta x. So that means that our volume, the volume of the approximating slice, is going to be pi r squared, which is the area of the circle, times delta x, which is the thickness. Right, so now what we have to do is we have to repeat the same process for each of the slices in which we have sliced our region. And so that means that we're going to add up all these pieces, and that brings us to the formula sum from 1 to n of pi r squared delta x. Now remember that I'm being sloppy with the notation here. It really should be an ri squared, so we're going to have a different radius for each of the slices, but all that complication is going to go away in the limit as we know, and therefore I'm dispensing with it. And again, once we go to the limit, all we have to do is take the limit as n goes to infinity of that sum. That means considering an infinite number of slices, each of them infinitely small, and that is by definition a definite integral. Which one? Well, it's going to be the definite integral from a to b, left to right, of our function pi r squared, and of course pi being a constant, it can go out, times the delta x, which is becoming the dx. So this is the formula that tells us how to compute the volume of a solid that is rotated around an axis, which is part of the boundary, so it does not create any holes in the solid itself, by using the method of disks. Well, what happens if we're still doing the same thing, but the axis of rotation is not a part of the region, but in fact is external to the region, so that we end up with a hole? Let's see.